And here we go. Okay, you know what? See if I can hide the video panel. And okay, yep, perfect. All right, let's try this.
Great.
All right. So we yeah, have about an hour. So okay, great. Okay, so we're going to cover several things on GenAI tonight. It's kind of hard. I was talking to somebody earlier. It's kind of hard to kind of pick and choose what to cover in generative AI because I feel like there's a lot of things to cover and you can go very deep on any one of them and spend hours. So I'll try to hit the high points for the most part, dig in on one or two things here and there. But if I do gloss over things, miss things, feel free to pop questions. I'll kind of stop it and work through. If I don't have time in the middle, I can definitely come back to them afterward as well. So we'll just kind of self-pace this a little bit and see how everything goes. I also was a little risky and added a couple of things this afternoon to the demo. So we'll see how that goes. Or knock on wood that the demo gods smile upon us tonight and everything works. So we will get there. Okay. And my clicker doesn't want to cooperate.
And if you want to be entered into the door prizes, come over and I can have it and have your email address and like you can hold it. And yeah, I'll drop it in the online chat as well.
All right. Oh. Oh, that's my I think because I'm sharing in Zoom and I've removed a lot of the controls, I can't like click my arrow key or move my slides forward. So I will have to literally click the slides manually. We'll operate on this though. Okay, I'm Jennifer Reif. I'm developer advocate at Neo4j. And I do a lot of different types of technical content. Really what it boils down to is I like to learn about technology and then I like to share that in a variety of different ways. I do a lot of tech speaking, tech blogging, tech podcasting. I recently am tech author, Java champion, and I do have hobbies outside of work, but I'm kind of a geek in a lot of different ways, and I kind of have fun with that. So that's basically what I do on my off time. My contact information there is in the lower left. It'll also be on the final slide. So if you think of something, often our best questions after the event ends, feel free to reach out to me. I'm more than happy to continue the conversation on tech, data, Neo4j, so on. Okay, now, at least when I came into the GenAI space as a Java developer, there were tons of very unfamiliar, very complicated sounding terms. A lot of these are traditional like AI ML terms or data science-y terms and mostly non-traditional developer terms. So a lot of this felt like a lot of upskilling, a lot of new terminology, and just a lot of new stuff. So we'll walk through some of the stuff as we go. I like to think of AI kind of in layers. And sometimes the more layers you add, the better your result. You think about like a croissant or like layered desserts. Sometimes the more layers, you get more textures, you get more flavors, you get kind of fun, new things. And that's kind of creative and fun. But at some point, adding additional layers doesn't give you any actual added benefit. Or sometimes that can even detract. So you think about adding too many layers to a croissant, it kind of compresses and flattens out. It's too heavy, so it doesn't fluff up and get, flaky and buttery. Add too many layers to a dessert makes it hard to eat. Sometimes you can't taste stuff or, one flavor dominates or the other. It just kind of tastes blah. So at some point, those added layers don't provide any added or enough added benefit. So you really have to evaluate what's the complexity here, what am I investing, and then what's the value I'm getting out of each stage or each step or each layer that I'm adding here. And once you hit the point where you do that cost benefit analysis and the costs outweigh the benefits, then that tells you to stop and go back a step and stay on that layer because that's where you get the best results and it's worth your time, worth your effort, worth your resources. Adding additional is just not enough worth there. So we're going to talk about AI and layers. The first layer just being generative AI as a whole general definition. Now, most of us probably are kind of familiar with what this is. This is actually a definition pulled from Wikipedia. It's probably been a couple of years back, but what I really like about it is it reinforces the idea that you send something as input and the generative AI model takes the patterns that it has learned and it creates something new that's similar based on its training data. So it's generating new stuff with similar characteristics from the input. So here's our first layer, the large language model. This is exactly what large language models do. ChatGPT, of course, came out in November of 2022. That's when it hit the market big anyway. Stands for Chat Generative Pre-trained Transformer. Many of us, and still I have trouble remembering exactly what all those acronyms stand for. But we have to remember that is a natural language response. It predicts the next word. It's a probabilities machine. It's a pattern matching machine. It doesn't do fact recall. It's not a search engine. You can do some feedback and reward to rank the responses. And we use it for pretty much everything under the sun, right? We'll talk a little bit later about some of the models that are designed for specific use cases, for particular domains or particular industries or what have you. But we adapt models for anything and everything, professional, personal, and anything in between. Now, let's start with a demo. I have slides just in case, demo falls apart, because it does. It's what happens. But let's start. I used to do this actually with ChatGPT, and then ChatGPT added web search capability. And the same demo just doesn't work anymore because now it can go out and search the web and find all its answers. And it doesn't really show off really what just an LLM does. So what I did is I created a Spring Boot app. I'm running Ollama, which is a local large language model, doesn't have access to any tools or external things. Oh, sure. I can zoom this up a little bit too. That might help. So it's a local model, doesn't have access to any tools or fancy other things. Capabilities. It's just the large language model itself. And let's see what happens when we skip stuff, just to kind of reinforce what this thing actually does. So I've got an endpoint out here, port 8080, and it's a chat endpoint, and I can send an input. Now let's just ask it something basic. Who is Jennifer Reif? Now I have a GitHub profile, I have social channels, I have my own personal website with blog posts out there, and have for quite a long time. Oh, that's a new one. Most of the time when I ask it this, it comes up with some sort of like American mathematician. Earlier, it came up with, I was a medical professional, I think it was. And now I'm a classical pianist. There, American mathematician. So there it is. I asked it again and it changed its answer. Okay, so why in the world does it do this? It's completely making stuff up. I know there's information out there on the web that it's probably been trained on about me. Why didn't it retrieve any of this stuff? And that's because it's not a search engine. It's a probabilities machine. It's a pattern matching. So it took the question, who is Jennifer Reif? Common requests or common questions out that on the data that it's been trained on of who is X. Probably celebrities, popular people, right? And people ask who that is. And then it probably took my name. It was like, well, what training data do I have that's similar to this name? And then it generated something new based on that training data, all those patterns that it had. And it came up with, I'm a mathematician. It's been kind of interesting because every time I ask it, it changes. I've worked at various universities. I've been 75 years old. I've been all sorts of interesting stuff. Now, okay, it's not great at this, but now let's look at another example where it actually does pretty well. So why is it that, if I ask it this, would you please create haiku about good and evil? And you've probably seen several questions like this. So please create a haiku about good and evil in the style of Yoda. So it actually does pretty well at this. And I've asked it to create a poem in the style of Emily Dickinson about technology. It did really well at that. Why does it do this so well? It's because it's been trained on patterns for haiku. It's been trained on patterns of all the text and the media that we have about good and evil and, entertainment, whatever else that's out there that's been trained on. And it has plenty of data on Yoda. So it knows how to take all these patterns and push them together and generate something new that's representative and has similar characteristics to those patterns that it has. So it's not fact recall, but it does really well at generating new from patterns.
What do you mean by fact recall?
Like a search engine, like asking it to, who is this, or what is 2 + 2, or it doesn't do like information recall or search engine type questions very well. So, what is pi? which it might actually do pretty decently at that one because there's enough data maybe on it. But anyway, so putting something in, getting the same thing back out is not predictable. Now, let's tweak this just a little bit. So let's say, who is Jennifer Reif? But now let's give it a little bit of extra information. Let's take my bio that is on this meetup's event page, and let's add that to the context. Who is Jennifer Reif, using this as context, and provide that bio. Oops. There we go. Okay, Jennifer Reif, developer advocate, Neo4j, speaker, blogger, MS and CMIS, passionate about technology, blah, blah, blah. Okay, so it did really well at this because I guided it and I gave it some information to use, and it was able to generate something new based on the information that I gave it. So it does really well when you provide it and add a little bit extra data and kind of narrow its search just a little bit. So that is what we are going to talk about.
Anything new though?
Huh?
Did it provide any new information?
I don't think it did because I told it to use that as context. And I didn't tell it to reference any other sources or like pull information together or, hey, summarize this or whatever. I guess the way I phrased it almost was like a factory call at that point. I'm providing the information. It's kind of tweaking the wording a little bit. You can see it kind of changed some of the wording and made it maybe nicer, more concise, whatever. And you could absolutely tell it to expand on stuff or make it more concise or do a one-line bio or what have you. And it does really well at those sorts of things. But yeah, I didn't ask it to add stuff, and so therefore it didn't. Sometimes it does, though. You got to watch that because it will. Okay, so I'm going to shut that down. And we'll switch and keep going. So these are just the slides in case the demo goes kaput, which thankfully it didn't. Okay, so we know that just an LLM won't work for most use cases. Most of the time, you don't want just to, generate a haiku about good and evil on the style of Yoda. That's not going to work. So what are some ways that we could maybe use an LLM, but kind of tack it on to existing things? And there are a couple of ways that you can provide additional context. One is you can train your own custom model. But of course, that's really expensive, very time intensive, and requires a lot of data science expertise and other folks. So that's probably not a great option. You'll have, large companies, very specialized use cases and stuff that might do this, but for the most part, it's not going to be feasible for the average person, average team, average company. You can also do some fine tuning or few shot learning, which means you add additional data and tune the model or prioritize the model's data and kind of added training basically is what you're doing. So you take the model, you give it some more training data, you tune it, you tell it what to prioritize, you tell it to focus on these things, and then it comes out and it's more tuned to that information. You can think of like us taking on a new training class or adding a new degree to our resume or something. It's going to specialize us just a little bit. That's kind of what fine tuning does. Few shot learning is similar, a little bit lower barrier to entry. You provide some examples to it, have it kind of use those as guidelines when it's searching and pattern matching and stuff in its system. And so that's another option. But again, you're still talking a lot of expertise, some time and resource intensiveness there. The third one, and the one that is most common, is called retrieval augmented generation, or RAG. Now, this is the one we're going to focus on tonight. But notice that all three of these involve training an LLM on specific data. So you're tacking on some specific data from something else and adding that to the LLM. Now, when I first came across RAG, it sounded like a lot of fancy terms all slammed together. And it is, but when you actually break it down, it really is what it says it is. So retrieval is data retrieved from some external source, something outside the LLM. Most often that's a database, but as we're going to see in a minute, it can be lots of different things. Then you're going to augment the large language model with that data you've pulled from the external source, which means added. If you're a former musician, that term will be very familiar. And then the thing that the LLM is actually really good at, which is generating a response in natural language. So taking that data, using it as source information, and generating a response or a summary or whatever you've asked it to do. Now, there's all different types of context. I mentioned that databases and all different kinds of databases are kind of the main one, but you could also source it and provide it documents or folders, various kinds of media, even charts, visualizations, and things like that. It can take and utilize those as context. Now, how do we start to provide some of these things as context really gets to be the question, because all of that information is various different formats. It's hard to navigate. It's hard to search. So what people have done is they've taken that data and they've represented it as an array of floating point numbers. They've vectorized it, which basically means you're converting data to an array of numbers that then represents a point in multidimensional space. It captures the meaning and how it's used, which is how it's semantically being used. We'll get to an example of this in just a second. But now, because we can take all different kinds of formats, think audio, text, video, anything else under the sun, images, we can condense this down to a numeric value that then we can compare and contrast and search and calculate and all sorts of other things. I always like to reference the saying, people used to say all the time, oh, you can't compare those two things, they're apples and oranges. Well, if I can sit down and look at any type of data and convert it to a series of numbers, now I can actually compare apples and oranges because I have a comparable format that I can use across both and look at, okay, these numbers are different and here's how they're similar because this is how they overlap and where they don't. So I kind of think it's funny that, oh, you can't compare those, are apples to oranges. Well, actually, we can now because we can vectorize it. Okay, now when I first came across this, it was like, oh, this is very mathematical. This is very data sciencey. How do we actually use vectors in the real world? What's the actual use case for the math? Apply it. Let me apply it. So a couple of examples that kind of relate to one another. So the one that I really like is the airplane example. So you think of three-dimensional space, start simple. And you have a path or a trajectory that you're flying in three-dimensional space, and you might have a wind that's pushing you off course. So you need to be able to calculate, okay, based on this wind, how fast it's going, how fast my plane's going, blah, blah, blah. How can I end up in the place where I want to go? But I need to calculate that new path based on the external forces and my old path, right? And we use vectors to do this. So we create a numeric representation of a series, an array of floating point numbers that represent that trajectory of the plane. We calculate those external forces in, and then we can calculate a new trajectory to accommodate for those. The Star Trek example is somewhat similar. But what I really like about this one is it's multidimensional space. No longer are you limited by three-dimensional space. You're dealing in multidimensional space. And you also have a lot more obstacles in outer space. Most of the time in the air, unless you're close to the ground where you can hit towers or something, you don't really have too many obstacles. In outer space, there's black holes, there's planets, there's asteroid belts, there's gravitational pulls, there's all sorts of things that might get in your way along that trajectory, along that path. And you need to be able to calculate new paths to go around and circumvent some of those things. So yeah, you wouldn't want to go through a black hole, obviously, that would be bad. So you'd have to calculate something new based on the old trajectory. Now, what Google did is they took this concept of vectors and they applied it to words back in 2012. This was their Word2Vec. There's a paper on it and library and all sorts of other things. But this example is really cool. And where this goes is now I can learn new concepts based on old concepts because I can do vector arithmetic. So for instance, you have a vector representation for king. So all of the features and characteristics that how we use the word king. You might think like leadership and wealth and a ruler and whatever else might go along with that. But then let's say I don't know what a queen is. So I could take the vector representation for king. I could subtract man, add woman, and that would probably give me something pretty close to queen, right? Because the way that we use king and queen is relatively similar. The biggest difference is going to be the gender. So I find this really cool because now I can look at new concepts and say, well, how similar is it to something that I already know? I did this a lot in music. I do this a lot in tech, right? We know something. It's like, well, okay, this new thing that I'm trying to learn, well, is it kind of like this or is it kind of like that? And I can do these calculations mathematically in the real world because now I can represent everything as a vector. And we have now taken this and applied this to data, all different kinds of data, text, images, video, etc. Now I need to be able to search that data. So I've vectorized it. I've created an array of floating point numbers. Now I need to be able to search it. You think about how many hundreds, thousands, millions, whatever, billions of entities we might have that we would want to search. And the way that we do this is with vector similarity search. We look at the proximity of things in vector search. The example I've started using that I kind of like, because I think subconsciously this was where my brain was going when I would think about multidimensional space, is in Star Wars: The Phantom Menace, Obi-Wan has lost a planet. He can't find it because somebody removed it from the archives. And so he sticks the little globe on the projector and it kind of blows up into multidimensional space. And he's like, okay, this is where the planet should be. There's gravitational pull and everything around it, but I can't find it. And it's been removed. But the multidimensional space where you have all these points, these stars, these planets, these, you know, gravitational pulls or whatever, that's kind of what I think of when you're looking at data in multidimensional space. There's all these kind of points and dots every which way. And I can calculate how similar things are based on the proximity of them in multidimensional space. So for instance, you know, similar star systems and planets will revolve around the sun. They have some things in common. They're going to be somewhat similar, right? And other things as well. So that's kind of where my brain goes on that. Maybe it's a little out there. The other example I like to use is that of a library. So right now in a library, you have kind of these narrowing categories that you search for. You have fiction and nonfiction, you have genres, you have authors, you have titles. And then let's say I might want to go in and find a new science fiction book. So I walk into the library, I go to the science fiction section. I just have to start pulling books off the shelf, hoping that it's something that looks interesting. I read the back cover, it might be something that I like. What if instead I could look for something very specific, a feature or a characteristic that I really like in science fiction books, and search based on that? And then it would trim out that result set, right, to something that's much more relevant and very specific to what I'm after. So much faster retrieval on that, very specific and highly relevant. Okay, so let's do a demo of this. I always like to talk and then show. So let's see how this actually works. So for that, I actually have a different vector. Yeah, there we go. A different app that I can start. And while that's starting, I'm going to show it so we can see the code. And all of this is available on GitHub. There's a lot of code out here. There's a lot of little things. Oh, and I forgot to switch my settings too. Give me 1 second. I'll zoom this in where it's a little bit easier. Here. Oops. And then one more spot. Here. I usually try to do this before the event, but I forgot. Okay. Is that okay? Can everybody read that all right? Okay. Sort of, maybe. Okay, so what I have in here is I've created another Spring Boot app, but this is using Spring AI, which is their AI framework, kind of like LangChain. LangChain4j is another alternate you could use for Java as well. And Spring AI is one. So I have a few things in the POM. First is to connect to, it tries to be helpful, to connect to Neo4j so we can run queries. I have where I can create several REST endpoints that I can interact with and showcase some of this. I'm using Neo4j as the vector store. We'll talk about that in a second. Neo4j is a graph database, and I'm just using it to store and search the vectors. Then I'm using OpenAI as my model of choice tonight. There's lots of options that Spring AI supports, so you can pick and choose there. You have tons of options. I'm just kind of going OpenAI run-of-the-mill default tonight. And then again, using Neo4j as the vector store. This is slightly different. This is providing some out-of-the-box advisors that you can use for RAG, which I don't end up using, but that's just kind of a default dependency that gets dropped in there. And then I'm also including MCP, which we'll get to at the end. But I'm using it as a client to connect to one of Neo4j's MCP servers. And again, we'll talk about that as we get down the road a bit. Okay, so the first thing that I do is I've provided everything as tools. So this is kind of an agentic approach where I've created a tool for vector search. I've created a tool for the MCP. I've created a tool for GraphRAG. And then we can access those and let the LLM access those. So I kind of have all these tools defined. I got the description, what they're supposed to do. They do the vector search and then kind of format the results and send that back to the LLM. And then where actually the rubber meets the road is over here in the controller class. So I've injected the chat client, which is going to use OpenAI to interact and with OpenAI as kind of like a chat. And then I pull in MCP for later. And then the vector endpoint, I set up kind of a prompt. Answer this question using vector search, use the vector search tool from that RAG tool class to find the relevant documents. And then it calls the LLM, in this case, OpenAI, using that prompt that we defined and the original question, which gets injected into that. And then it calls the LLM. And then what comes back is a large chat response object. So what I really care about is just the string answer that's coming out of that. So it's the content key that's coming back from that. So I'm just returning that because that's really what we want to focus on. Okay, so let's test this out. I know it's kind of a whirlwind, but let's see over here. Yes, okay. So I'm going to go into this. There we go. And then let's hit the /vector and let's ask it. Oh, I forgot to mention too. The data set that I have in Neo4j is SEC Edgar filings, which are financial filings of companies. It's commonly being used for a lot of, I guess, kind of RAG and GraphRAG types of demos. And I found this one to be actually pretty cool. It seemed a little, I guess, intimidating because like, oh, these are financial filings. It's kind of boring, but it gets kind of interesting when you start breaking this apart. So let's ask it something like, sorry, what are the risks that Apple faces? And let's just see what it has in store for us. So what this is doing, it's doing a vector similarity search, and then it's going to take those results, those Spring AI documents is kind of the entity that it gets dumped into, and then it's going to send that and the prompt over to the large language model. Now, what this says, the answer that comes back faces several significant risks: regulatory and legal, environmental, social, and governance, cybersecurity, supply chain, product quality, market economic risks, investment risks, etc. And we could go over to this tab here, and I've actually outputted the document chunks that it's referencing. Yes.
How is searching for the similar vectors that you mentioned?
Yes, so it's taking the, so the question that I send it, what are the risks that Apple faces? It goes out to the large language model with that question. It creates a vector representation of that question, and then comes back to the database and says, what are the most similar vectors to this vector embedding of the question? And it finds the most similar, by default, it's 4 in Spring AI, so it finds the most similar 4, and then returns those, sends those to the LLM with the original question. Does that make sense?
Can you explain this with example of in, queen, and woman bot?
So that was a word embedding. So what I'm doing now is I'm taking the, what are the risks that Apple faces as a whole question, and it's creating a vector representation of that. So it'll highlight specific features or characteristics within that sentence that it deems important, like probably the capital letter in A for Apple, or maybe the company of Apple, or maybe risks, or it breaks it down. And that is a very machine learning based algorithm that happens under the hood, for which is kind of a black box to me. But it does that calculation and creates a vector representation and an array of those features and characteristics that OpenAI has deemed important.
And search online or data sets or different models?
So it's searching my Neo4j vector store. So I've told it, hey, there's vectors out here. Go search all these vectors on these entities in the database, which I'll explain a little bit better in a second when we talk about graph and how it's structured. But it'll go out and search those vectors using the vector that it created for the embedding, or that it encoded for the question. Sorry. That makes sense?
Yeah.
Okay, great. Good question. Okay, so these are the chunks that are actually coming back. So we took these SEC Edgar filings, financial documents that are tens of pages long, and we chunked them up into smaller segments. And then we created a vector representation for those chunks. We saved that in the database. And then now we are searching those chunks from those financial documents based on that question that I asked it. Okay. So I could read these, but it's really dry and it would be long, right? Because these are large chunks. And you think about, huge documents and such, that would be really hard to go in and validate. And that's actually one of the problems with this. Now, one thing to kind of jump off of this is vector search doesn't always mean relevant. It's doing a semantic search, which is awesome because you're not restricted by the keywords and the tags that are in the data. However, just because it's semantically similar doesn't mean it is the relevant thing that I'm looking for in my question. For instance, the question that I'm asking, what are the risks that Apple faces? Sorry, wrong one. If I just show what's actually coming back from the vector search, the companies that are coming back, I have an endpoint out here called Vector Plus that is just going to showcase the company list that it's finding in the documents. And we'll see how sometimes a smaller subset returns highly relevant things, but a larger subset sometimes just kind of expands and goes past. So for instance, what are the risks that Apple faces? The first 10 documents it finds are all for Apple. That's good. It's great. That's relevant. That's what we're looking for. But now if we expanded it up to 20, it finds 18. And the first multiple are Apple, but down at the bottom, it finds Microsoft, it finds Amazon, it finds PayPal. Why is that? I asked it for Apple. Why didn't it give me Apple? That's because vector search is semantic search. It's not keyword. It's not looking for Apple and traversing out from that entity or that, piece of data or that document. It's looking at what are similar companies to Apple. So it's finding Amazon, it's finding PayPal, it's finding Microsoft. And it's pulling chunks of documents from that too, because they're semantically similar to the ones it's finding for Apple. So just because it's semantically similar does not mean it's always relevant. And sometimes you expand that search or you expand those horizons and pull in, top 50, top 100. All of a sudden, you're going to get things that aren't semantically similar anymore. So vector search starts much more broad, and then you can narrow it in. Yes, we'll kind of showcase this a little bit better after we talk about graph, because we'll do the vector search and then we'll kind of traverse from that point in. So let's step in and do that piece. Okay, so yes.
So is the demo size so that it can run locally on your machine? How many tokens per second is it processing?
So that would come back in the full chat response. It does actually show you, like if I return the chat response rather than just the string, it'll tell you how many tokens are being used. Now, because I'm sending like chunks of documents, that is going to extend that context out, and it is going to be more expensive, but it's also going to be much more relevant as well. So you do have to weigh that.
Is it all running locally on your machine in Llama?
So this one is using OpenAI, and my Neo4j instance is a sandbox instance running in the cloud.
Just that first one was?
Yes, yeah, the first example was using a llama because it was, otherwise if I used a public model, it references tools, calls, and a bunch of other web searches and things now. So it doesn't showcase it as well. So when I kind of limit it in.
So none of these kind of questions would fit locally on your machine?
Correct, because it doesn't have access to the data source. Now I could plug Ollama into my Spring app and then plug it into Neo4j and do RAG using Ollama. I've just found that OpenAI works well and it seems to do well, but I'm starting to dig into those local models a little bit more. And that's something that I hope to be able to start plugging in and pulling in and testing out some of these RAG solutions with the local models.
I was just wondering,
yeah,
this would be all, it's interesting. Yeah, I should get around to doing, I guess, but just sort of indexing everything on my machine. But I really don't want to send that all to OpenAI.
Yeah, and that's where something like a local model, your local databases will do that.
And those are fast enough? Like the AI puzzle with chips in Apple right now?
Yeah, so my machine has done really well. I think this is a M2 or M3 chip that's in here. But I've heard it runs really well on like M2, M1s, some of your newer chips that, are designed a little bit to handle these heavier workloads. Right. The results from the local models. Now, I haven't tested them myself. That's why I actually would like to get in and test them myself on some of these domains and stuff that I'm working with. But the results that I have heard is that the local models tend not to be as good as a lot of your big public models for this type of stuff. But again, I haven't dug in there and actually seen the results to be able to evaluate it for myself. That's just kind of what I've heard hearsay. But yeah, that would be something. I know a lot of people are needing to go to those local models because they don't want their data sensitive, or they don't want the models to have access to that stuff. And that's where your local models really shine. Or even some of your like open source models stuff too. Was there another question? Did I? Yeah.
The Neo4j is your RAGs?
Yes. Yes.
How
Yeah.
big is it?
Well, I can show it actually. I have the database pulled up.
How many documents?
Yes. So I have what ends up being, zoom in just a little bit, 2,100 nodes and 5,000 relationships in here, which I explain a little bit better in a minute. Let me see. There is a subset of, now this is just limited to 25, so hang on. There's 11 documents sitting out there, but then the chunk nodes, because we divide those, hundreds of pages or tens of pages up into chunks. So the chunk nodes, there's 390 chunks sitting out there. So it's
11 documents is 11 companies?
yes, 11 SEC EDGAR filings for like 11 companies. So there's 11 documents out there and then 390 chunks. So those 11 documents have been broken up into 390 sections, basically. So it is a little bit of a selective data source, just for, import and extraction purposes. So what we ended up doing was we took the documents, which actually I showed this in a second. So I ought to just stop talking and show. Okay. So the benefits of retrieval augmented generation with a LLM is you can kind of guide those probabilities with context. Think about the example where I asked it, who am I? And then added that context to it. It kind of guides those probabilities and narrows its search result set a little bit, which is going to make it a little bit more accurate by default. It's kind of hovering down that training subset it has to traverse. You can also add to the large language model's knowledge. Most large language models, even the new ones, have some kind of cutoff date for their training. It takes a lot of time and resources to train and prioritize and things like that. And so a lot of them, I think even some of the latest ones are cut off at like October of 2023. When you think about how much has happened in the last 2 years, all of the news, the media, the content, even just technology, how fast it's changed and the new documentation. And the large language model has not been trained on that information. So you could provide real-time content or updates or details that it doesn't have access to and it wasn't trained on. This is going to help, all of these things are going to help reduce that margin of error by kind of focusing it, by adding to its information and so on. And it also helps you trace back, how did the large language model get to this information? When I asked it, what are the risks that Apple faces? It could give me chunks of documents as reference and say, this is where I'm getting this answer. You can find it in these documents. Now, yes, it's hard to sift through and to verify, but you can kind of trace and figure out, okay, where this information is coming from. Now, the downside is that there's not a whole lot of metadata that you can add next to vectors typically. So in like traditional vector databases, if you will, you can add some connections, for instance, the companies or the forms or the assets or risks or whatever that might be in those documents. You could add some of that, but you can't add it all and you're limited somewhat because that's just the way vector databases are designed and optimized. They're really good at those vector similarity searches. It's also really hard to verify the vector representations. If I have the vector for an apple, how do I know that that's the vector representation for an apple? It could be anything under the sun. Humans do not read numbers very well and assimilate them with things or concepts. Can I explain how it got the answer? So when it went in and did the vector similarity search, how do I know that those documents are actually the most similar documents to that question that I sent in? It's a little bit of a black box. And then the question that we looked at, which was similar does not always mean it's highly relevant. For instance, if I ask something about an apple, am I talking about the city, the big apple? Am I talking about Apple the computer? Am I talking about Apple the fruit? Who knows? So it gets really kind of generic or vague depending on what you've provided. So there's other ways to now extend, adding on another layer of AI, extend RAG even further by incorporating some sort of retrieval on top of the vector search. So you do some sort of retrieval query, and that can be all different types of queries with all different types of databases, but you take the vector similar results and then you go out and pull additional information based on those results. One way to do that is by using a graph database. Now, what graph databases are is they help explain how and why things are connected. You can analyze the data from the relationships. So you get both the relationships and the entities in the database. It's designed for storing and navigating networks. It also makes it really traceable and explainable. For instance, the graph that I have kind of down in the lower right of the slide, if somebody's coming back with a particular side effect, they're dealing with a particular side effect, you can go back and understand, oh, this person had these symptoms, was diagnosed with this disease, therefore they were prescribed this medication, and therefore this medication is probably lending them these side effects. So you can trace and follow that customer or the patient journey really well in just this very small data set. Now, to look at another example, let's say I have two people, and I might want to understand how these two people are connected. So Jennifer and Michael. We might find out, oh, they actually worked for the same company, at least at some point in time, right? You can do a little bit more digging on figure out, okay, what were the days, were they there at the same time? Did they just, work at different years or so on? But then you might find out, oh, they actually went to the same school too. And again, you can do it, time comparison and figure out, okay, what's the connection there? How did they know one another? You go back a little bit further, oh, but they enrolled in 2 separate degrees. So they might have attended the same school, the same company. Maybe do they know one another? Did they attend the same classes? Did they not? Did they not even reference one another at all? And yet they have a lot of things in common. And then you might have other people who completed similar degree paths or degree journeys through that. Now, just through this, and you could also add metadata, properties, for instance, names of companies and schools and people and degree programs and so on. Now, what this allows you to do is answer a lot of different complex questions from lots of different points of view, just with this very small data set. For instance, from a company's perspective, how many coworkers might have shared classes or degrees? Do they have similar backgrounds? What are common degree journeys that people might take when they go through school? Do we have a lot of people kind of moving from, different industry degrees, or do we have a lot of people staying and moving on to higher education degrees? How many alumni come back versus new people coming in? And then let's say I'm a person at a company, and I might want to figure out people who might want to join my club, or maybe I want to start a club and find people who might want to be added to that. So I might look for who else has things in common with me. Do we have, same school, same background, same job description, same classes, same teachers, whatever it is that you might have in common. You can find those pathways through the network. Now, graphs are made up of nodes and relationships, or if you're familiar with mathematical term, it's vertices and edges. Your nodes are your objects or your entities. You can label those, which is basically like categorizing or grouping them. And you can also have properties, which is metadata, think key value pairs for extra information on those. Then the real value of graphs are the relationships, which connect the entities together. You have to have a relationship type, and you also have to have a relationship direction. So for instance, a person worked for a company, probably not so much the other way around, although maybe we would like it that way. And then you can also add properties to relationships as well. For instance, dates or start dates and end dates, maybe semesters or grade levels for classes and degree programs and so on. So graphs add context and meaning. They don't just tell you that things are connected. They tell you how they are connected. For instance, there's lots of different types of relationships that could occur between two people. This graph tells us this person is friends with this person. They don't work together. They don't have coffee together. They don't go to the same grocery store. They don't live in the same area. No, this person is friends with this other person. The other thing that's really cool about graphs is you can pull in lots of different types of data. So you can map structured data. You can also map unstructured data in Neo4j. The flexible schema provides a very natural fit for all these different types of kind of data structures, if you will. And you can document the connections and the paths among all those different types of data and connect those different structures. So for instance, this is actually the data set that I'm using tonight. So we've taken the documents, the SEC filing documents there in blue here. And then we've chunked those up and divided them up into smaller pieces of chunks. That's where we've created that vector and stored it on those nodes, on those chunk nodes. And then we've taken all the text from those documents and we've actually extracted entities, in this instance, companies, from those documents. So we extract the companies. And then we also extract any asset managers that are mentioned, any products, any stock types, any risk factors, and et cetera, that might be hidden in those documents. And we extract that structured data from the unstructured and pull those out into entities and connect them all together. It makes for a really powerful and really interesting use case. GraphRAG then is really just using graph as a data source in retrieval augmented generation. It doesn't need to be the only one. It just has to be one, and then you could stamp it and label it as GraphRAG. And GraphRAG will give you a little bit more accuracy, verifiability, and explainability. The reason for this is Neo4j uses this example a lot, where you have this human view of an apple. Now, many of us might view this apple slightly differently. We like it, we don't like it, you know, what have you. It's sweet, it's not. But most of us will agree it's a certain size, a certain color, it has certain factors like the stem and the seeds and the core and whatever else. But then the vector representation, most of us looking at that number would not be able to tell it's an apple or what type of apple it is or anything. The knowledge graph representation of an apple, you can document lots of different kinds of things. This one is an example of kind of the biology information of an apple. For instance, comes from a tree, it has a body structure, a color, a size, a shape, the kind it is, it's a fruit. But we could also put in things like the recipes it's used in or different recipes that it might be useful for. And then you could add that information to your knowledge graph as well, or any other type of apple representation you wanted to add to that, you can. That's the kind of the flexibility and the power of graph. All right, so let's look at now taking not just the vector search, we're going to tack on a retrieval query. So what we're going to do is we're going to do the vector search piece, which is going to search this unstructured information over here, the document in the chunk. Then we're going to go back out and do a retrieval query to say, for these similar chunks, grab the related documents, companies, and risk factors that are attached to that. So we're going to do multiple hops here. Pull all that information back in and add that as context to the prompt that goes to the LLM. Clear as mud. I guess let me show the code really quickly for this. So we have this graph endpoint. We see answer this question using the graph enriched search. So here's the question that gets added. Use the graph enriched search tool to find relevant documents with company and risk information. Then it's going to do the same thing that our vector search did, where it calls the LLM, passes in the prompt, returns the content answer. Now the tool for graph is sitting out here, and it's going to do the vector similarity search, but then it's going to take those results, the vector results, and it's going to pass those in to a graph retrieval query. It's going to call the getRagDocuments method, which runs a query in Neo4j based on those vector results, and then retrieves the related graph information coming back from that. It's going to format those, send those stuff those into the prompt, and then send that to the LLM. The query that is being run is here in the repository. So it's finding the chunks where they are in those similar document IDs that we found in the similarity search. Then it pulls the related documents from those chunks, pulls the related companies in those documents. And then actually down here, I'm also pulling the risk factors that are related to those companies as well. So it's kind of a multi-hop stage, kind of summarizing that all up and then providing it as context to the prompt. Okay, so if I run that, go back to our vector. Now remember, let's start with a good question for vector search. Instead of what are the risks, let's look at which companies are impacted by, let's look at like banking regulations. There's lots of other things we could look at, but let's start general. So we're going to ask for a very, very general thing that it'll be able to find in the vector search. And then from those general vector search results, it can traverse the specific companies, the specific risk factors that are involved in those.
Companies are actively engaged in the tax avoidance schemes.
Yeah. Oh, and that's the vector. Sorry, that's why it's retrieving documents. So let me look at the graph, which I'm sure all of that would be very well hidden within their financial filing documents. And that's another thing that this is really powerful for is uncovering some of the stuff that's kind of gets hidden and surfaced within this unstructured data. Okay, so some companies impacted by banking regulations: Apple, Microsoft, and PayPal. It tells you a little bit information about why that is and the things that go along with that. Now, if we wanted to actually look at the data that's coming back, I know this is a little bit of an eyesore, but we can pull out the company names for each of these chunks are also included. So there's PayPal. There's one chunk for the company of PayPal. There should be another chunk here. sometimes it's kind of sectioned out, which is nice, makes it a little bit easier to find. There's another one for PayPal. Okay, here's a chunk. So let's go back up to the previous one. Company Microsoft. So PayPal and Microsoft. So far, so good. And then last but not least, let's see if we can find Apple in here. There's the risk there, Apple Inc. Okay, so that is exactly what it surfaced. It found those chunks from those documents. It grabbed the related companies, Apple, Microsoft, PayPal, and then it grabbed additional information along with that. Okay, so it's pulling those back. So that's where it's getting that data. And we can traverse that through the graph by looking at the chunks and then grabbing the related companies that are in the relationships and then related other things that might be attached there. Now to kind of expand this further, we're going to take just a little bit of a dive into MCP very quickly, and then we'll jump back and wrap up. So one thing that's really cool, we've looked at examples where you can do vector similarity search, kind of start broad and move in. But what if you really just care about kind of doing very specific things within structured data? That's where something like text to cipher, text to SQL, text to whatever, you can ask it a very natural language question. It will generate the statement, SQL, cipher, whatever it is. In our case, we're going to use cipher, the cipher statement. It'll run that against the graph database and retrieve the results from that query. So this is something that's really good when you want to look at the structured data that's in the database. And you might not always know what types of questions you would be asked, or you want to provide a lot of opportunities for different types of questions. Let me show the code really quickly here. So I've provided it as a tool. Oh, wait, no, I haven't actually, because I have added it as an MCP server. So there's documentation on how to do this. I can show the web page later if you guys are interested. For all of our MCP servers, we have a bunch. So I just configured that. And then in the controller, so first thing to just kind of test that, I'm going to show all the tools that are available for the MCP server. I'll showcase that in a second. It just goes out to the MCP and says, hey, what are all the tools that are available to me to use within the Neo4j Cypher MCP server? Returns those back. And then the text to cipher piece is it says generate a cipher query for the question that you're going to send in. First, call the schema tool, then generate and execute a cipher query using the read Neo4j Cypher tool. Show the cipher query you're going to execute before you show the results. So it's a little bit explicit there. Sometimes you have to kind of guide it. This actually does pretty well, I found. And then that's all I think I need to show. So let's do a couple of queries here. All right, so let's start with something simple. Let's do 8080/text to cipher. And we're going to pass it. Let's say what companies are in the database. And let's just see what it does. Okay, so here's the cipher statement it put together. Match company, return the company name as company name. And the results are as follows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 companies. Let's verify this and see if it's actually right. So we can run this exact same query that it ran, hopefully. Okay, and I know it's a little bit hard to see, but you scroll down here, there are 12 results. It also shows it right here, 12 records that are being returned. So it found 12, that's exactly what it found, and that's what's in the database. So that's a good start. Okay, now let's expand this just a little bit more. Let's look for, let's see. What was the other question I was playing around with earlier? What 5 companies, if I could type, face the most risks? Let's see how it does with this one. And I've kind of tweaked wording. It may be very different every time. Okay, so company faces risk factor, return the name of the company, count the risks that it faces, order by the risk count in descending order, and limit to the top 5. So here are the results. PG&E, Amazon, PayPal, NVIDIA, and Apple. And you can see all of the risks that are linked in the graph database, the risk factors that are linked in the graph database for each one of those companies. So it does really well on this front. Used to, was a little iffy on text to cipher, text to SQL. The most recent models have gotten really good at this. Okay, so with that, I'll jump back in and just kind of wrap up here with a few other little things. Okay, so we've already kind of touched on MCP, we've already kind of touched on agents, but there's lots of other topics in this area. For instance, you can pick a variety of different large language models based on specialized use cases. So you have general large language models, you have code-based large language models, you have large language models designed for various domains and specializations and industries. Also memory, kind of conversation memory, chat memory has been a kind of major topic, and trying to understand how to help large language models retain context over time without getting too cumbersome, of course. Evaluating whether the prompts and the results coming back from large language models are good and valid. So kind of governing and guardrails and boundaries and things around that, and accuracy and testing. Of course, data ethics, data privacy, bias, and testing practices are all huge, very important topics that I think will continue to evolve over time. And then agents and tools. So we kind of showed a little bit of this, but there's a kind of a sliding scale of how specific or how process oriented you want the large language model to choose the tools versus how much control you give the large language model to pick and choose the steps and which tools to use and so on. So there's kind of a workflow practice or approach, and there's more of autonomy approach, and then everything in between. And then MCP, or Model Context Protocol, is a way to provide modular and consistent access to large language models to a variety of different services, data points, and so on. So lots of information that could be available there. Now, still remember, large language models are non-deterministic, and therefore, no matter how many times you input something, sometimes you just get a different result coming out the other side. So you can provide it A, and 7 times out of 10, it'll give you B. And then the other 3 times out of 10, it'll give you something totally different and way off base. So you still can't 100% control it, but you can guide it and improve that accuracy much better. And of course, you still have to figure out which model works best for your domain, for the use case that you're dealing with. You do have to do a little bit of prompt construction. I found that it's less sensitive than it was in the early days to how you construct your prompt, but still sometimes you have to be a little bit particular depending on what you're dealing with. And then of course you run up, the more data you add to you stuff into your prompt and send to the large language model, the bigger that context window gets, the more expensive it is, the bigger the tokens, the more it has to retain in memory and all that. So you do have to kind of work with that a little bit and try to trim that when it starts to become too cumbersome. All right, so before we wrap up, Neo4j has an free online and entirely virtual developer conference that it runs every year. This year's is happening in November. And it is basically 24 hours of constant virtual content. It is a ton of fun. It is one of my favorite events every year. There's 4 different tracks, lots of users, customers, internal Neo4j product stuff that gets presented there. So if you're interested in that, feel free to either scan the QR code or the neo4j.com/nodes. We'll kind of tell you all about that. And then I'll give it a second there. Okay, and then today's repository, if you want to look at the code, review, check things out, play with things, feel free to do that. That's that first link. The second link is another repository I have that kind of showcases a few different ways you can go about GraphRAG. So I have kind of just a very manual approach to GraphRAG. I have where I'm using Spring AI's question answer advisor, so some of their out-of-the-box RAG tools, and then also using RAG as kind of a tool calling where I do kind of the agentic approach to it, if you will. So you can check out that second repository if you're interested in kind of the differentiation between those. We do have several online free and self-paced training courses at Neo4j Graph Academy. So if you're interested more in how vector search works, how you can write your own chatbot over a knowledge graph, how you can do MCP stuff with Neo4j, all of those courses are available and free and self-paced. And then I also did write a knowledge graph ebook that is free for download too last winter. So if you're interested more in just how to construct Neo4j, the use cases, how it works, what it does, feel free to check out that ebook. Question. Sorry.
Doesn't Neo4j also give you a free smallish instance to play with as well?
Yes. Yep. So there's a couple of different options there. You can do our Neo4j Aura, which is Neo4j hosted or not self-managed, but it's Neo4j managed cloud instances, and there's free tier available for that. And then we also have Neo4j sandbox instances where when you go through like our Graph Academy courses, it spins up kind of cloud databases in the background that you can play with or add data there. And then there's the Neo4j desktop, which downloads like an application and you can run local instances within that. So there's a few options there.
Thanks.
And all of those options are free. Your question.
I was thinking your first thing.
Yeah.
You told me that you need to add some layers to get our result more defined and bottom it down. Can we do this thing on vectors? Suppose you give me that you search and it bring out 10 vectors and the end last two was Amazon and PayPal. Can we do something like work on that to bring out the relevant vectors for me?
Yes, so you can do something like filtering. So there's either pre-filtering or post-filtering that you could narrow it down a little bit. Now, the caveat there is that you include whatever you're filtering as metadata in the vector store. So for instance, if it's, Pinecone, Milvis, PG vector, whatever it is, you've included the company name alongside that vector representation. So that would be something you could filter on through there. But there's not going to be a whole lot of extra data you can add to that. And you have to define that model up front for the things that you would want to filter on.
We need to train the model accordingly.
Huh?
We need to train the model accordingly.
It's more like a domain, like a domain design on the application layer or on the whoever's building the solution. So the developers and data scientists that are building the solution. It would be less so for the model.
Are there any other layers more than graph or that's enough?
Yes, there are. I mean, there's lots of, there's different kinds of vectors. So I actually just found out about this recently that there's different kinds of vectors that you can store. So Neo4j focuses on dense vectors, which tends to be the most common, most popular. But there are things like sparse vectors that handle kind of other types of use cases. Most of your, I think, vector databases are probably going to provide those. I don't know that for sure. I know Pinecone does because I've played around with Pinecone specifically. But there's other types of algorithms and vectors and vector search that you can do. There's all kinds of MCP, so providing services and layers and tools. You can have it access and start doing tasks, for instance. So not just referencing services, but when somebody asks, hey, I want to book a vacation during this date and I don't know, try some new cultural restaurants. It can actually call a variety of other services and write data to those or get the reservation numbers and bring those back and drop those into your calendar. And I mean, there's all kinds of things you could just stack and stack and stack layers. It just depends on how complicated you want to get.
One thing major set the graphs would be solved. All have a unit that and just they can be bidirectional, right?
Yes. So you store the relationship in a particular direction, but you can query it either direction. So you have to pick a direction when you actually write it to the database. But once you write it to the database, you could query it either way. So for instance, like the company, let's say I want to find all the chunks that are related to Apple. I could go in and look at Apple and just say, okay, find the documents and the chunks that are, related to that. And I could query it backwards if I wanted to, or the opposite direction.
So, how does using Neo4j compare to using RDBMS for a vector store?
Yeah, so personally, I haven't dug in and compared a bunch of the different types, but where I don't think your vector search is going to be drastically different. Your vector stores, like specific, one and done vector databases, are going to be highly optimized for those semantic searches. So there are some use cases that vector database is the fastest vector search, and nobody else can compete because they've designed and optimized their models for a different type of data model, where vector databases have, optimized for the vector and the vector search. However, where you start getting into the different databases, your vector search capability is probably going to be relatively similar. But where Neo4j really excels is in those relationship hops. So for instance, like a relational database, you can jump, tables, you can do joins and things like that. It's not too bad. But where you start to get a ton of hops or very complicated subqueries and filtering and all sorts of things, that's where your relational databases is just going to start to slog a little bit. So when you're doing lots of hops, lots of that network, path trajectories, that's where graph is really going to excel. Now, there will be other things. If you're not doing a whole lot of hops, you're not doing a lot of those complicated things, relational is probably fine, and you don't need the graph. But when you're doing a lot of those traversals and multi-hop queries, that's when graph really shines. Yeah, so for instance, just the one we were looking at tonight, well, that's not even a great example. I'm trying to think of one that has like a bunch. Well, actually, a good one we go back to and reference all the time is like an organizational hierarchy. So where you might want to find, a manager and you want to find their, sub-employees 3 levels down. That gets really hairy really fast because you're sub-referencing the same person or company employee table or whatever it is. And it's potentially a very complicated, one-to-many or many-to-many type of relationship there. So graph is going to be, it's going to hop, person reports to person, reports to person, reports to person. And you're going to be able to filter that down and narrow that down where you're not having to index, how many hundreds or thousands of employees you might have.
Common graph databases that we can use.
I mean, there's a few out there. AWS has Neptune. There's Janus Graph, I think. Redis used to have one, but they shut theirs down. Yeah.
Cosmo supports Neo4j.
Yeah, Cosmos supports some graph. I've heard some kind of buggy things. Of course, this is from a Neo4j perspective. I've heard some kind of buggy things where when you support a lot of different data models, data structures. Right. It kind of gets a little hairy and it's hard to optimize on one particular one. So if you're doing lots of different types of models, lots of different types of data structures, that might be the better way to go. But if you really want to focus and really want to highly optimize, graph or relational, you're going to want to pick a specialized database for that.
What is MCP?
Model Context Protocol. It's just so people have been
Google it, I don't know too.
yeah, okay. Yeah. So people are defining it as kind of the USB plug for LLMs. And basically it is a way to provide consistent tools in a somewhat guarded, restricted way for LLMs to access. So for instance, like our MCP server, let me switch tabs here. We have a bunch of MCP servers out there, and I can see the list is kind of over here. It's a little bit small. So there's actually they've added more even just in the last couple of weeks. I knew of the Cypher, memory, Aura, and data modeling. So apparently they've added a sandbox and a GDS as well. But we have a bunch of them. And the Neo4j Cypher one, which is the one I was playing with tonight, there's 3 different tools you can access. Get schema, which is going to grab the data model from the database and retrieve that back as nodes and relationships. So it'll tell you the entity types in your database. And then the read, so it'll run read queries against Neo4j. And then you can do the write Neo4j Cypher, which is to write things to the database. There's several examples out there. My colleague Jason Koo has several videos out there that kind of show this tool and connecting it to something like Claude Desktop, where you can ask it, hey, create a node for this person, or now add the relationship to this, or, oh, I need to tweak this and update this property. You could do that all natural language and it'll run the Cypher behind the scenes for you. So that's something that now you don't have to create your own configurations to run Cypher against Neo4j or to grab the schema from your database. This is a standard modular piece. You can just grab the server that's already defined, that's Neo4j supported, that's official, and you can use it to do those things. It's already set up for you. So people do that a lot for services and things too, to just give LLMs access to a flight calculator or to calendar or something else. It sets up a consistent access point. that then a ton of people or a ton of departments or a ton of applications can use in the same way.
It gives you a table of schemas for the database.
So
What is this? Yeah.
this tool does, yeah, within the MCP server.
Is it external data source that?
Yep.
So you're all looking at for additional information?
It's a metadata source for actual RAG source.
I kind of like to think of it as like I kind of think of it as like a microservice. So you'll create like an API on top of a data store, and then somebody can query payments, and you'll get this consistent object for the last 3 payments in the system. You're kind of doing that, but you're setting up an MCP server that then a large language model can say, grab the latest 3 MCP or the latest 3 transactions in the database. But instead of creating your own microservice and writing the query and setting that all up, you've just got an MCP server that does it. And no matter how many applications go out and use that, it's reusable. It's sitting out there and running. And as long as people can grab that server, they can use that same system, same setup.
So it translates your prompts into this database.
This particular MCP server does. There's lots of different types of MCP servers.
So when you were showcasing was the queries from the MCP server?
From Neo4j Cypher MCP server. Yeah. So like GitHub has MCP servers, Microsoft has MCP servers, most of your service companies will have MCP servers, and it's just a way for you to access their services.
Using actual language.
Yes. Yeah. Good question.
Do you have any kind of certifications that we can pursue?
Yes. So we have a Neo4j developer certification, and then we also have I think is it called Graph Data Science or something like that? I have to look it up. 1 second. Let's see. Graph Academy. I don't know why there. This is what I was looking for. And then certifications. Oh, Graph Data Science certification. That's what it is. So we have the certified professional, which is general Neo4j knowledge. And it kind of walks you through. In fact, I just did a video a couple months ago on how to study for it, what things you need to know, and all that stuff. And there's a couple of community members that have written blog posts about how they studied and passed both certifications. So yeah, if you're interested in that, feel free to check that out.
Cool.
They're not meant to stump the chump. They're there to make sure you have kind of a base level in Neo4j knowledge.
Sure.
Yes.
Wow.
Yep.
Good to know.
Mm-hmm. Yeah. That's fun.
Yeah, that is fun.
I actually, to prep for that video, I had to go back and like take the exam again to make sure it's like, oh, I hope I passed. I haven't taken this in a long time. I did pass, but
What does Neo4j mean in the commercial?
lots of different stuff. So our common use cases are things like social or organizational networks, things like fraud analytics, so surfacing fraud rings or unusual activity, basically across the patterns of financial transactions. Identity and access management, so who should have access to what role, and what access did that give them to read, write, or do whatever other thing. Those are probably our big ones. But it always fascinates me, the interesting things that people are doing with Neo4j. I come across all kinds of unusual use cases all the time. Oh, another good one is recommendation systems. We do that a lot as well. Yeah. Yeah. Like product recommendation, or even like who you should friend next, or who you might want to add to your network. So you think about most of your social platforms, a lot of those are using like graph recommendations under the hood. But there is somebody that's actually, there's a couple of different things I always think of. One was using it to map the migration patterns of salmon populations in rivers, using graph for that. Another really cool one that's kind of near and dear to me, because I like outer space, is someone was using it to map the space junk and the debris that's in our atmosphere. So they can figure out, how can we potentially remove it, or how can we avoid it when we send rockets up into space, so we don't hit dead satellites sitting out somewhere. Yeah, I mean, it's getting to be, kind of crowded up there, I'm sure. Right. And they've mapped it all using Neo4j. So yeah, it's really cool. There's some really cool, interesting things out there. So there's a lot of geospatial like use cases for it. So mapping, so taking like a point in space and mapping that back to places and kind of mapping, where are the gaps, where might we, kind of figure out the clusters of things, that are a problem, or surfacing kind of not necessarily just the space junk, but looking at like communications flow through networks. I've seen cases where people are looking at telecommunications networks and they found that one little person was a bottleneck because they were passing information along. Or you might find, hey, this person's actually the central hub. And if we lose this person, we lose all connection with all these unusual departments or information flows and stuff. So there's all kinds of things that Graph handles well on that.
So it's good for geospatial.
A lot of use cases on that, yeah. Train networks. There's a lot of like, yes, yeah, there's several use cases out there for that. A lot of our community have done stuff on that. Even just mapping, like political regions and things like that throughout the country, or mapping the networks and for instance, like the London Tube, figuring out the fastest route from one station to the next station. All kinds of interesting stuff.
Yeah,